right, welcome back. We are now going to get into section 2.2, polynomial functions of higher degree. So now the first thing we're going to look at are the graphs of polynomial functions. So what are some features that we can expect from a polynomial graph? So one of the primary features is that they are going to be continuous. So continuous functions. So what does that mean? Well, first of all, there are going to be no holes in the graph. So it's not going to stop and start and kind of go off and have this gap in there somewhere. So that's one thing. Another important feature is that the graph should be smooth, meaning no sharp turns. So if we had something that looks like this, that would be a polynomial function, because again, there's no sharp turns or anything, and obviously it goes on forever and ever in each direction. But, so this would be continuous. But if we had something that looks like this, it kind of goes, and maybe it stops, it has a jump, that would be no good. And if it kind of hit a sharp point and then went off like that, wouldn't be any good as well. So this would not be continuous. So we just got to be aware of that. That's something that's important. No holes, no jumps, no sharp turns. So that's would be the characteristics. All right, what are some other things we know? Well, we have this leading coefficient test. So an aspect of graphs that is useful to know is how it behaves as x gets really small, as x moves to the left, and how x behaves as x gets really large, as x moves to the right. So by examining a polynomial function's degree, so remember that degree was that highest power of x in the function, if it's even or odd, that's going to give us some information about the polynomial function, the graph, and if we know what its leading coefficient is, remember that kind of helps if it's going to be flip-flopped or something, or reflected. So it might be positive or negative. We can determine how the function rises or falls as x moves to the left or to the right. So again, just looking at that end behavior, that's another way to think of it. End behavior. So what are the different possibilities? Well, so we first need our general polynomial function. So a sub n, x to the n power. So n is the degree, and the leading coefficient is a sub n. So again, that's just a number. So if n is even, so if we have an even degreed polynomial and the leading coefficient is positive, then the polynomial goes up to the left and to the right. So that's one. Second one, if n is even and the leading coefficient is negative, because it's less than 0, then the polynomial goes down to the left and to the right. So it's going down on both ends. If n is odd and the leading coefficient is positive, then it's going to go down to the left and up to the right. And then the last case, if n is odd and the leading coefficient is negative, then the polynomial goes up to the left and down to the right. So, and we kind of already know a little bit about this, because remember we have those parent functions that we talked about back in chapter 1. So we can kind of use that as a little bit of a guide with some of this. Okay, so let's look and describe that left and right hand behavior, or the end behavior of the graph of the polynomial. So we have our polynomial here, f of x equals 6x minus 9x cubed plus x squared. So first question, is the degree even or odd? Now, the one thing to be careful about is don't always go by the very first term in the polynomial. That's not necessarily the degree. You have to look at the highest power. So the highest power in this case is 3. So it is odd. So we have an odd degree. And what do we know about the leading coefficient? Well, what's attached to that x to the third is a negative 9. So it is less than 0. So a sub n is less than 0. So that's going to put it into our last condition. So we know it's going to go up to the left and down to the right. So up to the left and down to the right. Now again, I'm being pretty general as far as how you write it, but you can write it in words, obviously. So, all right, and now what about B? Well, first thing we notice is that the highest power is 6. So again, this is going to be an even degree. And the leading coefficient is a 9.8. It's positive. So a sub n is greater than 0. So that puts us into the first category. So it's going to go up to the left and to the right. Now, how could we kind of cheat a little bit with this stuff? And cheat's a strong word, but we can think of it in terms of our parent functions. Remember, we know what f of x equals x squared looks like. That's just our standard parabola. And what does it do for its end behavior? It goes up to the left and it goes up to the right. So that's kind of a way you can remember all even functions. They have to do that. They have to go up to the left and up to the right. But for an odd one, think back to our parent function f of x equals x cubed. F of x equals x cubed, remember, looks something like this. So we can see this one goes up to the right and it goes down to the left. So, and the leading coefficient's positive, so it falls right into this third category. Goes down to the left, up to the right, exactly what we show here. So if you use these as a little bit of a guide in thinking about end behavior, that'll probably help you when you do these larger types of polynomial functions. So, all right. Now, looking at what we have next, we got the real zeros of polynomial functions. So what do we mean by that? Well, if for any polynomial function f of degree n, the following two statements are true. So the first one, the function f has at most n real zeros. So, so if you have a third degree polynomial, we could have 3 zeros. And if you're not sure what I mean by zeros, we're going to speak to that in a second. The second one says the graph has at most n minus 1 turning points. Okay, well, what's a turning point? Turning points, also called relative minima or maxima, are points at which the graph changes from increasing to decreasing or vice versa. So basically, if the graph is going up and then it comes back down, that's reaching a high point. It's reaching a maximum locally. And then if it curves back up, it's reaching a minimum locally. So that's all they mean by turning points, is where does it reach a high point looking at a small region of the graph? Where does it reach a low point looking at a small region of the graph? So, and we're going to talk more about that as we go. So what are zeros though? How do we determine zeros? Well, there's 4 different ways we can analyze this statement. So when f is a polynomial function and a is a real number, the statements listed below are equivalent. X equals a is a 0 of the polynomial function f. So you're looking for a value of x where the function is equal to 0. That's essentially what they're talking about. And that's what they say in statement 2. For x equals a is a solution of the polynomial function f of x equals 0. So again, you're looking at where x has to happen in order for the function to be equal to 0. So that's another equivalent way to say it. The third one, x minus a is a factor of the polynomial function f of x. So that one might be a little bit funky, but we're going to explore that one later on. And then the fourth possibility would be to say that the coordinates a comma 0 is an x-intercept of the graph of f. And we've talked about that before. How do we find those x-intercepts? We got to know where the function, or where y, is equal to 0. So they all are equivalent. They all mean the same thing. So let's try a couple examples. Find any real zeros of the function. Now, so we got 4x to the fourth minus 20x to the third plus 25x to the second. So now one of the first ways you should always try to solve a polynomial is by factoring. See if there's something in common that you can pull out. And in this case, we can see that there are x's in all three of these terms. So how many x's can we pull out? Well, we can only pull out whatever the minimum is. In this case, x to the second is the minimum. So we can pull that out of all three of those. Now we couldn't pull out any of the numbers because, yes, 4 goes into 20, but 4 does not go into 25. So we couldn't have pulled out any numbers. So now for this one, we can see that if we're not sure if we factored it right, remember, all you need to do is just multiply it back in and see if it gets you back to the original. So you can do that pretty quickly and see that we get back to the original. Now we want to see if we can break it down any more. Now x to the second power, remember we are setting this equal to 0, so x to the second power times this is equal to 0. So that gives us two possibilities. That means that x squared has to equal 0, or we could say that 4x squared minus 20x plus 25 is equal to 0. Now this one's pretty silly because we know that this means x equals 0. But this one, well, this one we're going to have to try to break it down even more so we can factor it. Remember, factoring is the best way to start, but it doesn't always work. So if we're going to factor it, we're going to want two binomials that multiply out to give us this. Now, we can go through a lot of different possibilities for how to break this down, but I recognize that this is a perfect square trinomial. So I know that we can use a 2x here and a 2x there, because if I multiply those, I get back my 4x squared. As far as the 25, well, if we wanted to break that down, 5 and 5 is going to be the best bet for that. Now, we could go through, if you need to see how exactly I got to that point, you can ask about it, but there are techniques for factoring quadratics. That's essentially what we're doing here. But the last part of this is where this minus comes in, so we're going to need that in both of these. So remember, this sign tells you that they're the same, and this sign tells you what those two signs have to be. So when this is a plus, we know those two signs are the same. They're either both pluses or both minuses. In this case, they're going to be both minuses because that's what this sign is telling us. So now if we foiled this all out, we would get our original quadratic back here. So now to finish this one off, we can set each of these equal to 0, but it's redundant to do it twice. And so we do get x equals 5/2 for both of those. So now, since these are the same, we really don't need to write them both. But so in this case, we have two zeros to this function. Now remember, up here it says, boom. Up here it says that the function has at most n real zeros. So we can't go above that number, but we can be below it. And in this case, we are below it. We have two real zeros, and that's it, even though we could have had up to 4 based on the degree of this polynomial. So what about this one now? Well, we have a third degree polynomial. And now for this one, we do want to factor it, but there's a specific way that you're going to want to factor it. And the method's called factoring by grouping. So what we can do is group together our first two terms and the second two terms, and we want to separate them with a plus. So if we look at each of these two groups separately, we can factor those, and hopefully we'll see a relationship in what's left. So out of this first two, we can see we have that x squared is common to both, so we can pull that out. And so when we pull that out, all we're left with is x plus 3. So now these second two, well, we can see there's a negative on both of them, so that's common. But 4 also goes into both of those, so we can factor that as well. So we want to pull out a minus 4, and now the question is what's left behind? So negative 4 times what equals a negative 4x? It's got to be a positive x, right? And so now negative 4 times what is a negative 12? And that's got to be a positive 3. Now, factoring by grouping doesn't always work, and we're going to see later on in the course how we can look at different ways to try to break these things down when they get a little bit more complicated. But for now, we are able to do factoring by grouping, and so now look at what we have left. There's an x plus 3 that's common to both of those. So just like we pulled out the x squared on the first two and the minus 4 on the second two, out of this whole thing, we can pull out an x plus 3. So if we pull out the x plus 3, what's left? Well, if you remove x plus 3 from this whole thing, all you're left with is x squared. If you pull x plus 3 out of this whole thing, then all you're left with is a minus 4. So that would be the factoring. And remember, if you're not sure if you did it right, all you got to do is FOIL it back out. So multiply the first, the inside, the outside, the last, and that should get you back to the original polynomial. But from here, we can set x plus 3 equal to 0 and get x equals negative 3. Over here, x squared minus 4 equals 0. So how do we want to break that down? Probably the easiest way, because we just have those two terms, let's move that minus 4 over to the other side. So that's going to be a positive 4. And then we can take square root. But don't forget the plus or minus. Because remember, 2 times 2 is 4, but negative 2 times negative 2 is also 4. So we got to have both of those answers. So in this case, we do have 3 zeros. 1, 2, 3. So in this case, it does match the rule. All right, so this video has been kind of long, so I'm going to stop here, and then we'll pick up more on the next video. See you soon.